What is a relation? Just a set of ordered pairs, really. What makes a relation a function? What's the rule that can't happen, Rowan?
They have to be related by there has to be like some sort of, I guess, an equation, showing the relation between them and how.
Right, and there's something specific about the abisca. I'm not saying it right. How do we say it? The hibiscus? Not the hibiscus. Abscissa. That's what it is. Trying to be fancy and I'm botching it. Right? What needs to not happen with the x coordinates in a function? They can't be repeated, right? They can't be the same. Okay, so let's quickly get this down. So we know that a relation is a set of ordered pairs. So any set of ordered pairs is considered a relation. Your domain, remember, is the set of all the first coordinates of ordered pairs in the relation. You don't necessarily have to write everything I have on that board. It's your notes. Do what you want. It just makes sense. All the x values, write that down in your notes. Or if you think you have it, don't feel the need to write anything in your notes. That's up to you. Okay, so we know that the domain is the set of all the first coordinates of the ordered pairs in a relation, which then tells us that the range would be the set of all the second coordinates of ordered pairs in a relation. Okay, so we have a relation, we have the domain, we have the range. So what is a function? Well, function is a special type of relation. So a special relation between two variables such that each value of the independent variable, so such that each value of the independent variable there corresponds exactly one value of the dependent variable. Which we know is that as the range, right? So every x coordinate in our domain can only be paired up with one value of the y values in the range, right? And that's what makes it a function. This is just our fancy formal definition. All right, so you should be able to determine whether something is a function or not. So given a set of values, so if I had something that was like this, set of ordered pairs, 1, 2, 3, 4, would this be a function? No, because I have one duplicated, right? If we had it in a mapping diagram, 1, 2, 3, 4, 5, 6. If this one branches out to the 1 and the 5, That would not be a function, right? So it's easy to see it when we have a set of ordered pairs, or if we have it in a mapping diagram, or if I turn that into a table of values, it would be the same thing, right? 1, 2, 3, 4, oops, put 5 down here. So 1, 4, 1, 5. So it's easy to see it there. Where it makes it a little bit more complicated is when we have it written out as an actual algebraic model, or as a graph. Okay, so don't put this in your notes, just put this up here for my own purpose. So there's 4 ways to represent a function. We've talked about it graphically. Okay, numerically, we could look at it that way with just like a set of ordered pairs or as a table of values. Algebraically, so as an actual equation, or in words. Usually we have that when we're doing it in context. We talked about this before. Again, you don't have to put this in your notes. We're just going to bring some fancy vocabulary back in. We talked about implicit and explicit forms last class. It's just something we can add into our repertoire when we're talking fancy. So an implicit form is just any function that's defined with an x and a y. If you can solve it for your y, that means you can take it to an explicit form. No, I wouldn't write this down. You're not going to be quizzed on this. But if you hear me say the implicit form, that just means we have a function with x and y. If it's solved for y, then that's its explicit form. Okay? Domain restrictions. We talked about that in your homework. I would put this down in your notes. We talked about domain restrictions with real-world context problems. But now what's going to happen is we're going to have domain restrictions in 2 scenarios. First scenario, any values of x that result in division by 0. That's a big no-no. No dividing by 0. If you do that on your calculator, the world's going to explode, so don't do it. So any values of x that result in division by 0 will not be in the domain. So that's our first scenario we need to be worried about for domain restrictions. The second one is when we're dealing with square roots. So any values of x that result in taking the square root of a negative number will not be in the domain. So remember, when we take the square root of negative numbers, that results in imaginary numbers. And if we're talking in real-world context right now, we're not going to deal with imaginary numbers at this point in time. So we can't have division by 0, and we can't take a square root of a negative number. Okay, so that's where we will come up with domain restrictions. All right, is everybody good? Okay, so don't put this one in your notes because I feel like we have already taken care of this. What would be the domain of this graph? Well, our first x value is at -3, then -2, then +1. So just the set of -3, -2, -1. My range would be -3, -2, -1, 0, and 1, right? And I would just list that out. For this graph, we just did this on our Desmos. My domain would be what? All real numbers. How do we do all real numbers in interval notation? Maybe we should do a star with that. Yeah.
Isn't it like negative infinity?
Yeah, yep. So let's do a quick little star here in our notes. So whenever we have an answer of all real numbers, in interval notation, it is -infinity to infinity. So get in the habit of writing your answers like that if it's asked, if it's all real numbers, instead of writing out all real numbers. And I will not judge you on your infinity symbols because mine never are good. Okay. If we go back to that graph, I forget where the vertex was. Let's say it's at 2. What would be the range of that? Jillian?
X Is less than or equal to?
Yeah, so, well, it's y, because
Y,
range,
yeah.
right? So y is less than or equal to -2, so it's everything below. How do I write that in interval notation? Jalen?
All the, I forgot what it's called.
The infinity, negative infinity? Oh, the closed bracket?
Yeah, negative infinity
To 2. Good. Okay. So maybe you want to put this in your notes. So our range for this graph would be, if I start from the bottom, work my way up, because that's how I do range, smallest to largest. Well, the bottom, there is no bottom. So it keeps going down, 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 down forever. So it's going all the way down to negative infinity. We never, ever put a square bracket at that negative infinity, because I can never equal infinity. It's impossible. It's not an actual number. And I'm going all the way up to positive 2 square bracket. Okay, so interval notation. We should get in the habit of doing that. Okay, so if you have all real numbers, negative infinity to infinity. If you don't have a bottom, so if this was flipped up top, then I would be going from 2 up to positive infinity, right? Okay, so we've got that covered. Skip through. So now let's get to example 2 where we have our domain restrictions. Let's go ahead and do this one together. So we're going to find the domain of each function, then graph it to determine the range. So we have the function g of x is equal to the square root of x minus 3. So what did we say cannot happen underneath a square root sign? A negative number, right? So, does anybody remember the fancy word of what we call underneath the radical sign? The radicand. Does that sound familiar to you guys? So in this case, your radicand is the algebraic expression x minus 3. And we know that that cannot be negative. So that means that we know that it has to be equal to 0 or greater than 0, right? So we're going to take the radicand, which in this case is the x minus 3, and I'm going to set that greater than or equal to 0. So we know that it has to be 0 or positive. Can't be negative. Solving that gets us that x has to be greater than or equal to 3. So there's your domain. So my domain, I'm going to just use a D for domain. I'm working from smallest to largest. The smallest value my x could potentially be is 3, including 3. So square bracket on that 3. That's bad looking 3. And it's going to keep getting bigger and bigger and bigger and bigger and bigger. So it's going to infinity. What does that look like as a graph? What do square roots look like as a graph? Here's my x, here's my y. So at 3, we're at 0. So 1, 2, 3. And it's just going to go up like this. Right, just keeps curving up. So if I plugged in 4, that would put me at 1. So what would be the range of that graph? It's the lowest it can bottom out at. 0, and then it's just going to keep getting bigger and bigger and bigger. So we're going from 0 to infinity. Good. Okay, so domain and range of a square root graph. Good with that one. Try not to go too fast so your fingers don't fall off. All right. Next one, let's go to a rational graph. So same thing, part B. F of x is equal to x all over x squared minus 4. So whenever we have a rational graph, we know that we cannot have 0 in the denominator. So I'm going to focus just on my denominator and set that not equals to 0. So how can we solve that one? I'll add 4, square root it, right? So x squared not equal to 4, square root both sides, which means x cannot be equal to 2. Can it be equal to negative 2 also? Or not equal to, right? Plus or minus 2. So I cannot let x not equal positive 2 or negative 2. In set notation, this is really easy to write out. We can just do the set of all x's such that x cannot equal positive or negative 2. That's easy. How do you think we would do it in interval notation? So think about your number line. Here's my real number line. I have a gap happening at negative 2 and at 2. But everything else can be a solution. So if I just focus on this half, covering up this, how do I write this in interval notation? Well, my furthest left is negative infinity, and we're going all the way up to negative 2. So negative infinity to negative 2, not including it. This middle chunk is going from negative 2 to positive 2. I'm going to leave a gap there because we're going to put something there in a second. And then my third part is going from 2 all the way up to positive infinity. Again, I'm going to leave a gap there because I'm going to put something in between there. Do you remember what algebraic symbol we put in between these to bring them together? Helen?
Is it a U?
It is a U. So we're doing the union of those 3 sets of numbers. So that's how you would write it in interval notation. A lot easier in set notation that time around, huh? So it's every number except I have a hole here at negative 2 and I have a hole here at positive 2. All right, so get in the practice of doing that in interval notation. All righty. Okay, how do we graph that? That's a pretty funky graph. Let's get our calculators out. Can we do it on our calculator? The calculator's charging right now.
Yeah, it just came in.
Ooh,
It took
nice.
so long. It was on back order.
Turn my stat plots off. All right, so when we go into our y equals screen there. Now, what's really nice, if your calculator has it, if you hit alpha and second, is that what I want? Nope, maybe second alpha. Nope. Oh, goodness, how do I get it? I have to get my calculator. There's a way to, get fraction buttons. Is it alpha y equals? There it is, alpha y equals. Does yours come up with that menu? Yeah, and so it's really nice if you click on number 1, it's going to give you already the fraction bar, so then you don't have to worry about putting in parentheses around everything.
Wait, how do you do that again?
Alpha y equals.
Like, enter? And then you press more.
Does yours come up with that menu if you do hit alpha's y equal?
Equals, is it?
And then hit number 1. So if you hit alpha and then y equals, you should get this little menu.
What I was doing.
I got it.
We're doing y and then the equal sign.
Yeah, I was like, I don't
Come back.
Alright, that actually doesn't do anything.
It doesn't? All right, I'll show you what you have to do. So then you can put in, what was it? I forget what the graph was. It was x over x squared minus 4. So you can just type it in as you see it. If you don't have that, you're going to have to do x. So I would put parentheses around everything in your numerator. Divide it by parentheses x squared minus 4. So you just are going to have to group your numerators and your denominators surrounded by the division sign there. All right, do a zoom 6, see what that graph looks like. Let's look at our range. Our range. Do we have any bottom? Nope. Do I have a hole anywhere? Well, it looks like here we're approaching maybe 0 from here to here, but do I have 0 included here? Yeah. So would it be all real numbers? Yeah, it would be. So our range is going to be all real numbers.
Wait, can I see what you put in the calculator?
Yeah.
On the line equals sign?
Mine is probably.
Yeah?
I had a graph on my calculator.
Oh, she just did the same thing.
Oh wait, how do I do?
says draw.
Where's my defect?
What?
I just like actually get the graph. Graph 6.
Yeah, that's
Oh,
it.
or I just graph, I guess.
Let me see it. What'd you do?
Like,
And then
why?
it
It's
says
pretty-
draw.
That's what I think we're supposed to do 6. Oh, you're supposed to do 6.
Mine is on
Back out.
Zoom in.
Yeah. How do you zoom in? You press zoom and then
You press zoom, and then zoom in is number 2. So just press
I like it.
Yeah. I know, mine.
I just changed the.
It's not really a window.
Really?
How do you change the window?
Did
Is yours in color?
Yeah.
Mine's on.
That's what I just got.
I have the
You have the charger too.
4 plus.
Yeah, that's what I have. Mine just
If
arrived,
you,
so I'm
if you
charging.
press trace, you can actually read.
Why are they always so graphic? Oh,
I know, dude.
but I was like, might as well get the one also.
I know. And like also, like that'll last us for a while, I feel like, so.
It's like a phone. I was
Yeah,
using
I
it and
know.
I kept going like this.
What?
Why is my graph so... I know you can't.
Zoom 6.
I did that, it's not working.
Zoom 6. Just keep Zoom 6 in.
I was, and it doesn't let me do it now. I hit
Zoom
Zoom.
6.
Zoom in.
anymore.
Zoom.
But like, do you have press on nails on?
What?
Do you have press on nails?
Oh yeah.
I wish there was a back button.
I noticed
I can
them.
find out.
Oh,
Sorry.
No.
Wait, I can be so hot if I get.
I noticed them a few minutes ago.
Oh yeah, I was very excited about
You
that.
can't have,
I
didn't find time to do.
You might feel like borrow this
How much does it take?
and I'll give you one of these, and then.
Really?
Yeah, you just gotta pick out the ones that fit your nail.
I want to get nails, but it's not gonna go good with
I
nails.
think
I
it's
know.
Like,
I don't do throw-ins.
Dude, I was.
All right, everybody get it?
volleyball.
No, I won't zoom. I got stuck
What?
somewhere.
I know. I'm not bad. I was like literally like I should have.
Ruby just started playing this year.
Really?
Yeah. What?
Oh, because you have your X and
And
I was
Taylor,
like, wait, what?
and Taylor is good.
No? Why'd you say no?
Wait, how do I make
He
bigger?
doesn't
You don't
play a
really
lot of
play.
people.
I mean, I play any.
So just do Zoom 6 and it'll always take you back to like a normal 10 by 10.
Next to
Literally just started.
Just the whole time. Well, that's stupid.
Yeah, after you use
Literally
the
also
minus sign and
using
not
like
the
an
sign. Yeah. All right, so we got our calculators.
Weird.
All right, let's see. What else do we need to get through here? Let's go through some function notation quick. Oops. Before we get out of here. Oops. So given a function, can you guys evaluate the function in different ways? So we're going to just do a whole bunch of different function evaluations with the same function. So we have f of x is equal to 2x to the third minus 3x. And we're going to evaluate a bunch of different functions. All right, so the first one, we have f of 2. So plugging in 2 for our function in each spot gives us 2 times 2 squared minus 3 times 2. Again, I just would throw it all in my calculator instead of thinking, but if I had to think, 2 squared is 4, times 2 is 8, 8 minus 6 is 2. So f of 2 is equal to 2. For part B, so now we're going to take our function, the original function of 2x squared minus 3x, and add what we just evaluated, which would just be 2. So that's all our answer is there. Not too crazy, huh? Looks hard, but it's not. Everybody good? Okay, C. Let's evaluate f of 2x. Which just means we're going to double everything in our function. So 2 times 2x squared minus 3x, which gets us 4x squared minus 6x. Will be the negative of our function. Just flipping the sign of everything. So negative 2x squared and a positive 3x. Okay. We're running shy on time. We're always running shy on time in this class, huh? I'm going to jump to these last two here. So f of x plus h, and then we're going to do the difference quotient. Is everybody good? Okay, so for G, everywhere I see an x, I'm going to put an x plus h. So we have a 2. I'm going to do x plus h squared minus 3 times x plus h. Squaring that, it's going to get me x squared plus 2xh plus h squared. That's just foiling, rewriting it twice. Do I need to go through that? Then we're going to double everything there. So 2x squared plus 4xh plus 2h squared. Minus 3x minus 3h. So there's our answer for G. Now for H, we're just going to add an extra component. And this is called the difference quotient. This is a big thing in calculus. So if I were to subtract the original function from this, and then divide it by h, let's see what happens. So I'm just going to continue off of this. I'm going to subtract the original function. So I'm going to subtract a 2x squared, subtracting a negative 3x becomes a plus 3x. I'm going to divide that whole thing by h. So notice your 2x squareds cancel out. Your 3x cancels out. I come up here, I'm running out of space. So I'm left with just a 4xh plus 2h squared minus 3h divided by h. What's going to happen to my h's? I'm going to be able to cancel one out from each of these. So I'm left with just 4x plus 2h minus 3. That's our final answer there, with h not being able to equal to 0. Okay,